Hi, Dr. Pushkin. This is Nicholas Moya, and I'm presenting my project for your EE 472 Digital Controls class. So, for my project, I decided to build a robot that implements obstacle avoidance control using PID control. So, for the basic model, the robot uses a beagle bone black for inputting sensor values and judging distance and controlling the DC motors. Then it has two IR sensors that judge the distance between an object on the left side and on the right side of the robot. And then it has two DC motors, which of course control how fast the robot moves and whether it turns left or right. So, explaining this in state-based variables, I have them listed right here. So, x1 is the distance from the left sensor. x2 is the distance from the right sensor. And then x1 and x2, of course, is just the next distance from the left and right sensor, respectively. And u1 and u2 are the control PWM signals that are sent to the DC motors, which controls how fast they go and where they turn, and et cetera, like that. So u1, again, is left, u2 is right. And lastly, y1 and y2 are the ADC values that are read in from our sensors, and that, of course, corresponds to left and right also. This is y1 and y2. And using these state-based variables, I was able to develop a state-based equation to represent this robot. So here's how it works basically in a behavioral kind of situation. If the robot is too close to an object on the left, that is, the distance here, x1, is very small, then it controls the right motor, which is u2n, to decrease. That way it turns right. And this is represented in this equation. The next distance on the left is equal to the distance on the left plus the control signal sent to the right motor. That way the right motor controls the left distance. And the same is true for the other side. If this distance is very small, the robot controls the left motor to go slow down. That way it turns left and avoids this obstacle. And again, that's represented by the same sort of equation. The next distance on the right is equal to the distance on the right plus the control of the left motor. And then for the output variables just correspond to the sensors and their distances. So y1 is the ADC value read from the left sensor, which corresponds to the distance here, and then y2 is the ADC value read from the right sensor right here. So this is the state-based equations that I use. So, and here's the matrix elements. I left in my report how I derive these elements. The only important thing to know is that they're all 2x2 matrices, which mean, of course, that we have a MIMO system, which of course makes sense because we have multiple inputs, which is the distance right here, and multiple outputs, which is the PWM values that's sent. So another important thing to consider would be controllability and /reachability. For this case, controllability and reachability are the same because the A matrix is invertible. And so just looking at what the control matrix goes to, we can see that it is in fact full rank because the first two columns of the matrix are linear independent. Thus this is full rank, thus it's fully controllable. And the same similar thing happens for observability, that two of the rows of this matrices are linear independent, so this is full rank, so it is fully observable, which we expect because it actually works. And so now I'm going to go into the PID control section. So using past knowledge, I knew that it'd be better to just use PD controller because whenever I integrated I into my past robotic experiments, the control never worked. So this is actually just a PD controller, and here's how it works. So the error is calculated between what the distance is subtracted from a distance threshold. And in this case, it's like 25 centimeters. So that means the error is the difference between the distance we have and the distance we want. And then, oops, never mind that. And then the PD, PI, and the P and D values are calculated as the KP constant plus times that error, and the KD constant multiplied by the difference between the current error and the last error. And then using this PD, we set a motor speed, and this will be like our correction motor speed, and that is sent to the corresponding motor. And so this is basically how it works. This case right here is specific for when the left distance is below the threshold. And then there's another case when it's the same for this, when the distance on the right is below the threshold. And I can show you that right here. Yeah, so this is the corresponding case when the right distance is below threshold, and it does the same thing right there, only switching left and right variables, of course. And then the other two cases are when both the distances are greater than the threshold, which means that the robot isn't close to anything. It sets the speed as constant. And then the last case is if both the distances are below the threshold, which means it's too close to on both sides, and there the motor is set to off, and here 100 is off. And so using this PD controller, we're able to establish some cases right here. Here's the conditions for when the robot works. So just explaining what I did over there, just illustrating this idea. If the left distance is too small, it's smaller than the threshold, it controls the right motor to decrease. If the right distance is below threshold, it controls the left motor to decrease. If both motors are below the threshold, both of these stop. And if neither one of them are above threshold, or if they're both above the threshold, then they just go constant. So there's only two cases when control is actually implemented, and that's when the left distance is small or the right distance is small. So now I'll show you an actual demonstration of it working.